Good morning. This is Professor Grenfell's Math 12 Statistics class lecture. We're continuing today in Chapter 3, Section 2, discussing variation of a data set. And one remaining thing to talk about is the coefficient of variation. There, coefficient of variation. For a sample, we have different notation, but we'll call this C-var, or coefficient of variation, and it shall be the standard deviation of sample divided by the mean of sample. So it is S divided by chi-bar, and then we express that as a percentage. The population, it is effectively the same exact thing. If we wrote it out in words, we would say the coefficient of variation is equal to the standard deviation. So for a population, that's sigma divided by the mean. And so again, for a population, that is mu times 100, so that it is re-expressed in the form of a percentage. All right, just a quick example of this. Let's take a look at example 3-23. So this is pertaining to automobile sales. It says the mean number of sales of cars over a 3-month period is 87, and the standard deviation is 5. So that's what I've got recorded over here for our sales. And then the mean of the commissions is $5,225, and the standard deviation is $773. So here is the information for these two different data sets. Now, we can compare the variation. We can see, or we can determine the variations of these two data sets and see which set is more spread apart, more varied. Okay? So for the sales, the coefficient of variation, C-bar, how do we do that? Well, that would be S divided by chi-bar. All right. So remember, always try to write it down from your memory. Oh, and then times 100. I always forget that part. Okay. And that's the nice thing here too, is you write it down from memory. But if you feel uncertain, by all means, go look it up when you have those opportunities, right? Unless it's on the test. All right. So here we have a standard deviation of 5. We have a mean of 87, and then we're going to take that decimal value and re-express it as a percentage. Let me just go grab my calculator. Okay. So that decimal is approximately 0.057, and so we'll round that. After multiplying by 100, it's 5.7. We'll round that to 5.7%. Okay. For the commissions, let's just say COM, right? Our coefficient of variation, C-bar, is going to be the standard deviation divided by the mean. Let's forget that, times 100. Okay. And so this will be 773 divided by 5,225. Times 100 to convert that decimal that we will get into a percentage. And so that works out as 0.148 approximately. So that is 14.8%. Okay, so the next concept that we're going to talk about in Chapter 3, Section 2 is what we call the range rule of thumb. Hang on one second. That should be not an equal sign, but approximately equal. And we'll say capital R divided by 4. So the range rule of thumb is not an exact rule. It is a rule of thumb. In other words, it is an estimate. Okay, it's close, maybe, but not exactly. And what is this saying? This is saying that for a data set, the standard deviation, that is S, is approximately equal to whatever the range is divided by 4. Okay, this is a very crude estimation of what the standard deviation would be. If we just go ahead and examine the data that we had from example 3-20, or well, 3-21 as well. Here it was the number of teacher strikes at a public school district in Pennsylvania, something like that. We had 9, 10, 14, 7, 8, 3. We computed the standard deviation for this. We already did this in the previous example. We got 3.6 rounded. Okay, let's see what the range rule of thumb says. So it says here the standard deviation S is going to be, well, not equals, but approximately equal to the range divided by 4. So the highest value in our data set is 14, the lowest looks like it's 3. So our range, real quick, would be 14 minus 3, also known as 11. And here we're doing 11 divided by 4, and that works out as exactly 3.75. Okay. And so notice here, it's actually very close. In most examples that you look at, the range divided by 4 is in the same ballpark, but it's usually not exact. So that is what we mean by a rule of thumb. It's so a way of estimating it, doing it as a quick calculation, but you won't necessarily preserve a whole lot of accuracy. Okay, the next item under discussion, we're talking about the variation of a data set. We have to look at what is known as Chebyshev's theorem. So yeah, this is not only a nightmare to pronounce, but it is a little bit complex as well. So before we even begin to look at Chebyshev's theorem, I just looked ahead to the previous example, and what it is saying, well, what it is talking about is the proportion of different values that are close to the average value. And if your data set is very densely distributed, the number of values that are close to this average value is going to be a greater percentage. If it is more sort of spread out, then there's going to not be as many values, proportionally speaking, or in terms of the percentage of data values that are close to the center. It could be differently distributed. And so that is what Chebyshev's theorem speaks to. It ties together the average and the standard deviation and gives us a mean of talking about, well, how typical is this data value itself? So to get a grasp on what Chebyshev's theorem is talking about, let's suppose we have a data set where the average, the mean, is 50,000, and sigma, the standard deviation, is 10,000. Now, without knowing the shape of this distribution in terms of how the data is distributed, in terms of the density at which the data is distributed, we're just going to kind of talk about this as a concept. How many standard deviations are we away from the average value? So in general, we're going to be we're going to be distinct from the average by some amount, okay? And the standard deviation, also referred to as the standard error, is essentially a measurement of how typical we would assume that we are apart from the average, the mean. And so here, since the standard deviation is 10,000 and the mean is 50,000, here mu plus 1 copy of sigma, that would be 60,000. Oh, extra 0, that makes a difference. mu minus 1 copy of sigma, that would give us 50,000 minus 10,000, so that would be 40,000. Okay. So here, if I say everything in between 40,000 and 60,000, that would be considered to be within 1 standard deviation of the norm, or the average, the mean. Okay, so if I say, what is this range from 50,000 to 70,000, and then on this side from 30,000 to 50,000, notice this. If I'm saying this whole spread from 30,000 all the way to 70,000, what would that be? That would be, notice I've got on this side 2 copies of sigma. This is 2 times sigma, also known as 20,000. Right? On this side, I've got a distance that is exactly 2 times sigma, the length of exactly 20,000. So here, what would we be looking at? We'd be looking at taking mu, the average or the mean, and adding on 2 copies of sigma. That would give us 70,000. If we subtract away 2 copies of sigma, that would give us 30,000. So here, we're going to be thinking about how far away from the average value are we, not just in terms of the sheer absolute length, but in terms of how many copies of the standard deviation are we away from it. It's going to be essentially kind of like our standardized score that we attribute to this distribution. So what Chebyshev's theorem says, the statement is that the proportion of values within a data set that are within k standard deviations of the mean, this is at least, so I said it's greater than or equal to 1 minus 1 over k squared. So let me just go ahead and clear this for a little bit of space here and kind of illustrate what we mean here. So like I kind of had illustrated previously, here's our x number line. Let's kind of shift to an abstract viewpoint where I'm not going to tell you exactly what the mean is. I'm just going to say, there it is right in the middle. There it is. And I'm not going to tell you what the standard deviation is. I'm just going to say, here it is. This is, well, plus 1 copy of the standard deviation. This is mu minus 1 times sigma, whatever it is. This is mu plus 2 copies of sigma plus 3 copies, and so on and so forth. Now, the only restriction is, let's see, k has to be greater than 1. K has to be strictly greater than 1. If k is equal to 1, then this formula right here, if we plug in exactly 1, that would become 0. So we don't want that. That means when we're looking at our x values along the graph, we're going to be saying that the mean mu, that's in the middle. If we only go 1 standard deviation away, Chebyshev's theorem is not going to tell anything to us. It's not going to give us anything useful. So here, I have marked on this mu plus 2 sigma, mu minus 2 sigma. So for this range of values from mu minus 2 sigma all the way to mu plus 2 sigma, the coefficient that we have in front of the sigma is k. So here, if k is equal to 2, this proportion, 1 minus 1 over k squared, is going to be exactly 0.75. So the proportion of values that falls within this range, okay, whatever the lower threshold, whatever this value comes out to be, mu minus 2 copies of the standard deviation, all the way up to and including mu plus 2 copies of the standard deviation, that would be 75% of the data values. That it would be the proportion. If we go all the way out to 3 standard deviations here, I didn't mark it, but that would be 3 extra copies of sigma added on. And to this side here as well, if we go extending above and also below by 3 copies of the standard deviation, that produces a value of approximately 88.9. So say round it off there, so that it is to the nearest tenth of a percent. 88.9% of the values are going to be within 3 standard deviations, and so on and so forth. So basically, what we will be doing in order to find the proportion of values that fall within a certain range is we will first be looking to see how many copies of the standard deviation is that away from the average value. So in example 3-25, it's talking about prices of homes. It says the mean price of houses in a certain neighborhood is $50,000, and the standard deviation is $10,000. Find the price range for which at least 75% of the houses will sell. So notice here, they're telling us the proportion. The proportion that they gave us is 75%. So we're going to set that equal to 1 minus 1 over k squared. That's what Chebyshev's theorem is telling us. It's setting the minimum percentage of values that will fall within this range is 1 minus 1 over k squared. So we'll set up this formula right here and use this to solve for k. Well, this is a very common value. Anytime you have 75%, that is k equals 2. Anytime you have 88.9%, k equals 3, and so on and so forth. So here, we're going to be looking for the whole range of values that goes from 50,000 plus 2 copies of the standard deviation, right, all the way to 50,000 minus 2 copies of the standard deviation. And so that range is going to be from $30,000 to $70,000. That's our crude estimate for the price range, where at least 3/4, at least 75% of the home prices are going to be within this range. Another usage of Chebyshev's theorem is example 3-26, talking about travel allowances. I'll read the scenario. A survey of local companies found that the mean amount of travel allowances for couriers was 25 cents per mile. The standard deviation was 2 cents. Using Chebyshev's theorem, find the minimum percentage of the data values that will fall between 20 cents and 30 cents. So first thing, notice our average is right there in the middle, and this distance from 25, or this difference from 25 cents up to 30 cents is exactly the same as this difference from 25 cents down to 20 cents. So that always has to be the case whenever we're using Chebyshev's theorem, or else we have to kind of do more tricky stuff. The interval about the mean that we're looking at has to be symmetric. We have to have the same distance above as we do below. Okay. Now, what we have to do is we have to figure out this difference, which is 5 cents. How many standard deviations is that? So we're going to take that distance, 0.05, 5 cents, and divide by the standard deviation, 2 cents. And so that reduces down to 5 over 2, which is exactly 2.5. And this is what we found for k. All right. So k, remember in Chebyshev's theorem, was the number of standard deviations that we are away. So here we calculated that we are exactly 2.5 copies of the standard deviation away from the average, both to the upper side and to the lower side. So here, like we can kind of think of it like this. This is plus one copy of sigma. This is one more copy of sigma. And that would be half of a copy of sigma. So there we have 2.5 times sigma. And in Chebyshev's theorem, it says it's fine if k is not an integer. It's not a whole number. That is perfectly acceptable. The proportion is still going to be the same. We're still going to do the same calculation. So we're going to have 1 minus 1 over k squared, and we're substituting in 2.5 in place of k. And so the calculation for Chebyshev's theorem works out as 1 minus 1 over 6.25 is the same thing as $1 minus 16 cents, or, well, 1.00 minus 0.16 gives us 0.84. And as a proportion, that is 84%. So here we're saying at least 84% of the data values will be between 20 and 30. Now, the last little thing from Chapter 3, Section 2 is what we call the empirical or the normal rule. And this has to do with when we have data that is normally distributed. Or another way of describing this is the histogram looks like a bell-shaped curve. Notice I'm not drawing the actual histogram, the actual bar graph. I'm drawing this as kind of a smooth, more continuous version of that. But that is, if you want to just think of the histogram, just pixelate it, make it into a bar graph. If our bar graph or histogram or frequency polygon or the graph of the distribution is approximately bell-shaped like this, then we have a different proportion of values that are going to be falling within the center. So here, if our data is normally distributed, then 68% of the values are estimated to fall within just one standard deviation. So notice we can't even plug in k equals 1 into Chebyshev's theorem. And so this is already saying a lot more than what Chebyshev's theorem says. Chebyshev's theorem applies to any data distribution, whereas this one has to be more concentrated in the center. If that is the case, at least 68% will fall within one standard deviation, within two standard deviations. So from here, mu equals 2, mu plus 2 to mu minus 2, this range right here, 95% of the data values will be within that range. And then within 3 standard deviations, we estimate that 99.7, so almost everything is going to be within 3 standard deviations of the mean. And so that is where we will conclude for Chapter 3, Section 2. And we'll move on next time to measures of relative position, z-scores and percentiles and such in Chapter 3, Section 3. So stay tuned. Bye for now.